your estimated mean, which your hypothesis says is 0, and then dividing by the standard error. So that's where all this information is coming from. Does that make sense?
Do you think we need to go ahead and do that?
No, you can just
kind of plug it or
this is just kind of so you understand what these numbers are. You don't have to do this on an assignment because it's given to you anyway.
Where does x2 come from? You said 0?
X2?
You have 0.0146 minus 0.
0.0146?
Yeah.
That's the slope. So that's the beta 1 coefficient.
Right. Minus 0, where is it?
0, where is 0 coming from?
Yeah.
So that, that's just what they always use. They're always testing whether the coefficient is equal to 0, because if it's not equal to 0, that means it's statistically significant, and that it actually means something. Because if beta was 0, that basically the null hypothesis is that there's no relationship between x and y, which would mean that there's no slope, and you would just have a line. So you have x and y, and there's no correlation between them. And x doesn't influence y at all. And so that's what your null hypothesis is, and that's why you're using 0 there. And then also, in part 2 of part B, it's asking you to test the null hypothesis that beta 1 is equal to 0. And so that's always what this null hypothesis is that they do in regression outputs, is testing to see if there's no relationship between x and y. But we can reject that null hypothesis clearly because 14 is way out here in the reject zone. And so that's telling us that we have statistically significant results and that there's clearly a relationship between x and y. And then, okay. And then part 3 is asking about the 95%.
Can I ask a question?
Yes.
You just said that we're always going to be testing if that basically that the slope is 0. So your null is always going to be beta 1 equals 0.
Yes.
I can apply that to everything.
All regression output.
Okay.
Yes.
That makes like seem like it might be easier to move forward.
Yes. Yeah, that's what this test is always doing.
Okay.
Yeah. And so part 3 is asking, what is the 95% confidence interval of beta 1? Does this include 0? And so this is stuff we did all the first half of the semester too, but with the equation. So you have, in this case, it would be beta 1 plus or minus z times the standard error, basically. And then, so you would plug, but in this case it would be t, because we're using a sample instead of the population. But they give us this answer as well in the output. So we can see right here that that is our confidence interval. So if we had plugged in 0.0146 plus or minus our t-statistic of 2.26 times our standard error, which is 0.0009, we would get that our confidence interval are those two numbers, basically. And so that is telling us, the interpretation of this is that we're 95% sure that the population beta is within that interval. And so that's a fairly close interval. It's 0.012 and 0.016. So is that like, this is correct within like, is it $2,000 at that decimal place? Because it's in millions of dollars. But anyway, so it's a pretty tight confidence interval when you're thinking about it in terms of millions of dollars. And so basically, I'll turn off this stuff. So basically, this tells us real-world significance. This tells us statistical significance. And this shows us the range that we're confident that this number is correct, basically. So we're 95% sure that the real number is within those bounds. So that is basically what all the regression output tells So are there any questions about part 3 there? Okay. Okay, and so part C is saying, does the regression line look like it fits the data well? And that we kind of already talked about. It does look like it fits the regression line well because all the data points are really close to the regression line. You can't really picture a better line drawn through that data that you'd be more confident in, because this one fits the data really well. So that's kind of the thing you want to say for part C. And then part D, what percent of the variation in bets can be explained by attendance? And so that's asking about the R squared, which in the regression output is going to be right here. And so that's a really high number. Like for most regression, like in academic papers, it's pretty standard to get more like 0.3 because you never have all of the variables that explain a certain phenomenon. Like if you had student achievement and all these other variables, like most papers I've read with that, it's under 0.5 is the variation explained by your model. So this is a really high R squared, but that makes sense for this model because attendance obviously has a huge impact on bet size. I mean, it's pretty an intuitive result.
So this is saying that it has 96%.
Yeah. So 90
effect, or 97, I guess.
97% of the variation in bet amounts on a given day is explained by the attendance in the arena, is what that's telling you.
And you would expect all of this to change if you started adding in other factors, right? Like weather or something, or no?
I mean, you would expect it to change a little bit, probably. And R squared, well, so R squared, the number of variables you have in your equation, the more variables you add, the higher your R squared will be, just because you have more explaining what's going on in your Y variable. And so that's why you have the adjusted R squared, which he hasn't talked about yet, but it basically punishes you for adding in too many variables that don't matter. And so that's what economists call kitchen sink models, where you just throw every variable you can into the model so you can get a really high R squared. But the adjusted R squared punishes you for throwing in variables that don't matter. But I don't know if he'll get more into adjusted R squared or not. But R squared will always go up when you add in more variables. But even if you're adding in variables that aren't statistically significant in any way. So yeah, so does R squared kind of make sense in how you would explain that? Okay.
So an R squared